Gopal is presenting his talk, Fast and Efficient Climate Risk Estimation of Global Asset Portfolios. Take it away.
All right. Thank you, Sarah. I am in the midst of figuring out this tool, and I think you folks should be able to see my screen now. Okay, Sarah, can you just say you can see it?
Yes, we can see your screen.
Okay, thank you. Yeah, just want to make sure I'm not talking and not letting you folks to see. So welcome everyone. Super excited to be here and be talking at Machine Learning Conference again. I was a presenter in 2018 when the world was a much different place, and I was at the San Francisco location. So I'm still in California, and I wanted to share with you, I updated the title of the talk to be scenario analysis because I felt like that's more relevant to this crowd, and talking about scenario analysis using global climate models. So a little bit about myself. I spent the early years of my career working on multimedia products, worked on some interesting capabilities in spatial audio and video codecs. And in the last 5 years, I've been largely looking at geospatial data, looking at satellite imagery, looking at other forms of climate, as well as, and in my most recent role prior to SUS Global, I was the head of analytics and insights at Planet Labs. As a few of you know, Planet operates the largest constellation of Earth observation satellites. And my last talk at MLconf was very much around that, which is how do you use those Earth observation data sets towards creating large-scale information signals on the world and being able to serve that at scale as actionable insights. So at SUS Global, our goal is transforming the frontier climate science into actionable climate intelligence. And in the next 15, 20 minutes, we don't have that much time. My goal is to talk climate intelligence with you. I'll give you a landscape overview of what climate tech is. And from that, kind of focus a little bit more on scenarios, the latest climate models, how that interacts with the novel geospatial data sets, and then give you a few case studies on how this data can be used for actionable climate intelligence, and then get to what we at SUST call asset level geospatial analytics. So that's kind of like what we want to cover in the next 10, 15 or 20 minutes. So if you have any questions, feel free to throw it in the chat. We'll address it after. So the climate tech landscape, there's a lot going on in the space. It's one of the most vibrant areas of research at the moment in the context of data, machine learning, near real-time sensing. And broadly, I like to categorize the climate tech landscape into three buckets, right? There is the components of understanding risk. We are all aware of how the evolving climate creates some specific kinds of risks in terms of hazards, in terms of exposure. And when it comes to bigger organizations and defining policy, a big part of that translates to more transforming their understanding into something which is more in the context of planning. So how do you plan for the risk? And then there is the element of dealing with, coping and adapting to the changing climate, which is more in the context of disaster response, in the context of carbon capture, in the context of carbon sequestration. There's a lot of technology and new capabilities getting built up over there. So the focus at SUS Global has been largely on understanding and planning for risk. We serve financial institutions, city governments on the capability to be able to look at long-term forecasting of the climate and understand how that impacts their tangible assets on the ground. So when you look at understanding the changing climate, you're dealing with largely three kinds of slight variant data sets. So on one side, you have these large historic catalogs of exposure. So dating back to NOAA and hazard data sets around what's the exposure of varying temperature, of varying physical hazards like cyclones, tropical storms, floods, fires, heat waves. And then, that's the historic catalog. There's also the live event streams of active physical hazards happening all over the world as we speak, which could be, active fires, could be active floods. And then connecting that into forward-looking projections. And that's kind of where largely the climate modeling landscape seems to connect, which is getting the historic data, using that for inference on forward-looking climate. And in the context of climate intelligence, all these three are equally important. An understanding of the historic and the near real-time data helps you better interpret the forward-looking projections. And looking at the projections helps you infer on like patterns that have occurred in the past. So that's roughly like the three data components. And you hear the word scenarios a lot, and like I feel it can be a little confusing. So if you look at the naive definition of scenarios, they're like postulated sequence of or development of events. And one simpler way to say it is like scenarios are just like a grouping of assumptions made on the future. So when we talk about that in the context of climate, aka climate scenarios, they're like a grouping of possible social and economic pathways between now and the close of the century. So climate is a fairly complex beast. When you're talking climate, you're talking about a natively global phenomena. You're talking about a natively long time horizon evolution of like the variables. And in order to accurately project into the future, you need to take into account the social interactions, the economic policy, as well as like the additional forcings that go into what kind of modifies the Earth's subsystems. So that's like the cryosphere, the land masses, the oceans, and the air and the atmosphere. So that's kind of what broadly is called the climate scenarios. So, you probably all heard some version of this from someone, which is, you see a lot of ice, so there shouldn't be that much global warming. And that ties natively into our understanding of climate, which is it's fundamentally global and it's fundamentally long-term. And XKCD kind of like had a very good example of this, which they featured a few years ago, which is there's someone talking to the other saying it's so cold and it shouldn't be global warming. There's still so much ice. But the reality is, if you look at the historic perspective, it gives you a way towards calibrating what you're seeing today or in the last few years compared to what happened in history, and gives you the trends into the future. So in the context of climate scenarios, one of the and climate modeling, one of the bodies, which is the preeminent body for like research in the space, is the Intergovernmental Panel on Climate Change, the IPCC. And in the last 5 years, they've created a fairly comprehensive framework by which the climate projections and climate modeling across many different research labs all over the world come together under a common framework, and that's the CMIP-6. So the CMIP-6 stands for like the Coupled Model Intercomparison Project, and it kind of defines different social and economic scenarios that allow you to create the bundled together projections which are mapped to similar scenarios. So there are three scenarios that you'll hear about a lot in the context of climate, which are instrumental towards interpreting forward-looking projections. One of them is the SSP1. It's called the Green Road. So if we as a society take the right steps towards adaptation and mitigation, that's where we end up by the close of the century, which is an aggregate 2.6 watts of additional energy in the Earth's subsystems. And that keeps us at like a green path, which is the least amount of like extreme hazards, the least amount of global warming between now and the close of the century. The middle of the road is somewhere where we're placing some significant emphasis on adaptation, but it's still not like the extreme where we're doing getting to the green road. And the one in red is where we currently are projecting ourselves, because it's like to great extent the worst case. We aren't doing enough on climate and climate adaptation. And that's a business as usual scenario, which projects an upwards of 8.5 watts of additional energy in the Earth subsystems, and that's what's called SSP5. So the climate research that's happening in the world is tremendous. There are all these research institutions all over the world that are contributing to the CMIP6 framework of projections, and significant amount of research in almost all continents, which is very encouraging. And a big part of this is like, how do we get that research out into something actionable to understand what's the climate risk to the assets that you own, what's the climate risk to the assets that the organization you work for owns, what's the climate risk to the regions or the city governments to which you pay your taxes. So that's kind of like the broad way to look at it. So here's one example of projections from an Earth systems model from one of those research labs that I had on the map earlier. So this kind of looking at warming in degrees centigrade between the beginning of the 20th century and to the close of this century. And what you see in black is kind of like the projection based on the historic data from this specific model. So you can say that this is inference which can be tested. And what you see in different colors is inference that is projected under these different socioeconomic pathways or the SSPs. And what you can see is like, in the business as usual case, it's very clear, like we're on to some significant warming, upwards of 5 degrees. And if you go into the more conservative and the more green road paths, it gets closer to 2 degrees, which is what I mentioned earlier. So this could be, this is broadly like the realm of climate intelligence, which is looking in history and being able to understand just from warming, how are we calibrating to projections from a model. And normally this tracks pretty well because that's a data you can validate. And then as the months go by between now and like the next year, you can calibrate to like the more recent data that you collect, and then help you calibrate better and characterize the performance of these models over the long term. So, I've been talking a little bit in terms of warming and temperature, and it's kind of abstract. So I want to get to a couple of case studies, which could be interesting examples. So, from the fundamental variables like temperature, precipitation, and extreme precipitation and humidity, you can then project out the extreme hazards through more sophisticated physical hazard models. And one of the most significant physical hazards that emerge from climate are wildfires. The direct impact into the human settlement ecosystem, and the Pacific Northwest in particular has been like an extreme case. So you've all heard of like the wildfires in California over the last couple of years, and this year in particular. Earlier this year, like in September, the sky in San Francisco is like orange. Those of you who were here might have found that as like a truly remarkable phenomenon none of us had experienced in recent history. And this is kind of like a great summary of where things land. So there's a graph from NASA which shows the cumulative fire detections across the Pacific Northwest, and for every year in this century. And you can see that in 2020, you had like the cumulative, fire detections to be higher than any other year. And it's not just higher than just any other year, but it's also significantly higher. It's almost twice what we saw in 2018. And that's as of end of September. And we know in October, there were still fires in like Southern California. So this is real. There's a real-time manifestation of the changing climate and increased temperatures, increased dryness in specific parts of this region. And here's a simulation from the CMIP6 business as usual scenario of what you see across the Pacific Northwest in terms of monthly fire detections. So this using those models, ensembling the outputs from many models which are part of the CMIP6 across this specific business as usual scenario, and then mapping that into burnt area across grid cells. And thereby you can see what the projections look like between over the last 5 years, which allows you to calibrate against observed phenomena. So enter satellite data, and there's the MODIS data set, which is also a satellite from NASA, which allows you to look at what the observed fire detections are. And what you see is if you map that out over the last 5 years, the amount of fire detections is much higher than what a CMIP-6 business as usual scenario tells you. You can also see the increased fires, not just in the Pacific Northwest, but a big part of Siberia in Russia. And that's, there's not that much human settlement there, but there are many active fires. And that you can see through observed satellite data, because it maps out active fires more effectively. And this is from the MODIS Mod 14A1 data product that's been transformed and mapped to create this visualization. So this gives you a sense of the state of the art. You can project out physical hazards like wildfires into the future. You can also map that to observed phenomena over the recent past to see how well they calibrate. And that allows you to have more accurate projections into the future. So another example is if you look at like the MODIS observed data over August 2020, you can see the fires in the Pacific Northwest. You can also see the fires in Alaska. And both these locations, they kind of give you, they're a tale of two regions. So in Southern California, we've seen a consistent amount of burnt area over the last few years. And if you look at the climate models, they project something very similar. Between now and close to the century, there's like approximately, give or take one standard deviation, you're getting like 3.3% burnt area in that specific grid cell. And that's still very high. And if you look at a region, by contrast, if you look at a region like Alaska, you see not that much fire today from the models, but over the course of the next 8 decades, you see an increased amount of burned area. And that's a function of how the models work across the scenario. When you have increased warming, you have increased melting of the permafrost in Alaska, which exposes more land, which makes it more exposed to dry and warming scenarios, which create more projections for fires in the future. So that's kind of what you see, like, in Southern California, where you see like a lot of fires right now, like the fire footprint is expected to be something similar. But in an area where you don't see that many fires in the last several years, and where you're beginning to see the fires, you're seeing it increase rapidly over the next 8 decades. So that's kind of a interpretation of the forward-looking climate projections. Again, long time horizon, global phenomena, which have a fair bit of locality to it. So all locations are not the same when it comes to these sort of projections. Another case study that I wanted to just mention is that of flooding. Just like wildfires, flooding is also a huge disturbance to the human ecosystem and the human settlement in different regions, especially in parts of like Western Africa, where there's increasing need for better infrastructure, more development in the rural areas, and a growing population. So this is kind of like the max flooding exposure that's mapped from those same CMIP models over the business as usual scenario over the next 30 years. So it indicates there are some regions which are definitely having significant flood exposure over the next 30 years. And again, these are probabilistic estimates. There's no guarantee that there'll be a flood in a specific year or a specific month, but you can, over a course of like a longer time window, you can predict with a fair bit of certainty around what the level of flood exposure could be. And that's this mapping. Now, if you look at like the western part of Africa, it's home to many metal mining sites. And the environmental hazard around metal mining activity is one of the biggest sources of conflict between mining companies and the local population, because it connects into their water streams. Mining requires a lot of water. Secondly, it connects into their local ecology. It connects into the economic stimulus into these regions. So it's an area where there's a fair bit of like give and take between mining companies and the local population. And here's like a mapping of like mining sites across this specific region. There are active, inactive, and reclamation sites. And across each one of those, there's a certain amount of flooding exposure. So that's where you can spatially join this kind of flood exposure with like the mining. And the reason why this is important is For the mining companies, flooding is like a huge disruption, because normally when there is flooding, that also creates flooding in the mine sites, which also creates disruption to the work, because you can't mine any longer. The mine gets flooded. You got to wait for it to dry or get the water out in some other way. The other aspect of environmental hazard, which is more, in some cases one can argue is more significant, is the environmental hazard from the flooding and overtopping from tailings dams, which have a fair bit of toxic material. When you extract metal from the ore, you also extract a fair bit of toxic waste. Getting rid of that toxic waste is non-trivial. Normally they're stored in dams where they live for like a very long period of time. And when you have flooding or extreme precipitation, those dams kind of flood and overtop, which is they just get filled and there's no way for it to seep out. And then it leaks out into the local water streams. So that's another huge environmental hazard. So these sites are high risk when there is flooding. And if you look at two specific locations, one of them is an active mine in Mali, and the other one is inactive mine with a big tailing dam in Gabon, and both of them show you the flooding probability that is projected from one of the climate models as part of CMIP6 over the next 8 decades. And that gives you a sense of, both of these are fairly significant flooding probability. The one in Mali is very high, which means there's a very high likelihood that particular mine has disruption over the next couple of decades. And there is also a very high probability that there is flooding in the next 20 years around this specific location of an inactive mine, where there is the possibility of the water getting contaminated due to overtopping. So that's another scenario. So in the grand scheme of things, what I tried to highlight with those two examples is the fact that natively, when you talk about climate intelligence, you have the historic data, you have the early warning, event streams, and then you have these forward-looking projections, which are indicative of what the future looks like across different scenarios. And that's all global and natively interconnected, and with a fair bit of variability across regions. And when it comes to city planning, or when it comes to an individual, an organization, or like a region trying to understand the risk they have to climate change, it's normally at like a much smaller resolution. It's not global. It's more at the asset level, which is what's the exposure of my home or my community to wildfire, floods, cyclones. That's kind of like the beginning of like our interest, because it impacts each one of us. And that also impacts the business decision-making around organizations which have tangible footprint. So in order to connect these two, you need a way towards going from the global exposure maps into asset level risk assessments. And you do that through asset level geospatial analytics, the examples of which are what I just walked through. And in order to make that happen, you got to traverse the positional uncertainty, because when you go from global to asset level, you need much higher positional certainty. You need to know with a higher degree of confidence whether there's going to be an extreme hazard at your asset location. And then there's the element of temporal uncertainty, which is as you look, 3 decades out, 4 decades out, there's higher uncertainty in the risk projections. And you look at the next few years, there is a little better certainty, because you have a better understanding through historic exposure and early warning on what the forward-looking projections can mean. So in order to bridge these worlds together, you need to be able to bring the state-of-the-art climate models, the most active and bleeding edge climate data streams, as well as like the event catalogs and help analysis at the local level. And that incorporates elements of statistical learning, spatial inference, the ability to create metrics that are interpretable not just to machine learning folks or data science folks, but to business analysts and risk professionals. And then package that together into simple interactive tools that folks all over the world can use and make meaningful decisions with. And that's kind of what we're focused on at SAS Global. So if these areas are of interest to you, that's definitely something that I would love to talk to you more about. And this is one of the most important and pressing challenges in our society today. And we're seeing the ramifications of climate change as we speak, with the active fires and floods in different parts of the world. And this is an area where this community, the intelligence around machine learning and being able to interpret, analyze, and make decisions on data can really make a huge difference. So with that, I just wanted to conclude. Definitely feel free to get in touch, say hello. We're always hiring. We have a bunch of open roles that we're looking for to hire in the next few months. And if these kind of data streams are of interest to you, always interested in talking. So I just want to thank MLconf for this opportunity and for the chance to share an introduction to climate models and climate scenarios and how that can make actionable intelligence a possibility.
Thank you, Gopal. How climate change affects our future and understanding the risks associated with climate change should definitely be at the forefront of everyone's mind, including businesses.